So the point of this tutorial is to show you how you can use Excel to fit data using the solver feature. So what I have here is some real data that's been measured, and it doesn't matter what it actually is in this case. It's Y data versus X data, and here are the values that are actually being plotted. And so that is the measured data. We can't change that. Our aim is to fit this data, and we'll say that it looks like it's an inverted decaying exponential. And so here's the equation of a decaying exponential. And so we're going to attempt to fit this function to the data that we have. And if you were to do this using the built-in Excel solver features, you might be able to get away with it. However, if you had a slightly more complicated mathematical expression, there's absolutely no way that you could do this. And so the advantage of sort of hacking your own fit method is that you can adjust the equation that you're fitting to any physical situation. Okay, so we'll start by noting that in our equation we have three fitting parameters, A, B, and C. And presumably these are useful constants that we want to know for the physical world. So C would traditionally be like a relaxation time. B would be an amplitude, and A would be sort of an offset for the data, and that could be sort of the measurement of background noise. Regardless, we set up a table that has all the fitting parameters we need for this expression, and these are the parameters that we're going to allow Solver to adjust. So then our next step is to actually construct the fitted values of the function, and so we'll call that the model value because it's modeled by the equation. And here I'm just going to enter the formula for this equation. So A plus B times the exponential of negative C times X. And if I forgot that negative, the parameter C would be fitted as a negative value, so that's not crucial. What is important here is to make sure you put the dollar signs on the fitted parameters so that each cell in the Y model column references those fitted parameters. And so we've got the equation set up properly, and I'll just propagate that through all of the data. And again, I'm using the actual measured X values to fit the data. So now the next step is to calculate the difference between the modeled data and the real data. And because that difference can be positive or negative, we square it. So that difference is just this squared. And again, I'll propagate that through. So the final step here is to use Solver. You can't ask Solver to minimize each of these square differences. So what we're going to minimize is the sum of squares. There we go. So there's our sum of squares. Okay, so we look over here, and here's the data, and the orange line is the model, and it looks nothing like the data, and that's because it's not inverted. So let's invert it. All right, there we go. We've got the right direction of shape. We might want to raise it up a little bit. Maybe a little too much. Let's see. I'm just going to kind of play with these parameters and try and make it look a little bit more like the curve that we're actually fitting. And the reason I'm doing that is because this is a non-linear fitting algorithm. There's a lot of local minima that the solution can get trapped in. And so you want to choose parameters that are as close to the real value as possible so that you don't trap your solution into one of those sort of spurious minima. All right, so at this point we're ready to apply the solving algorithm to fit the data. And so that's through Solver. And the cell that we want as our objective is the sum of squares, and we want that to be a minimum. In fact, yeah, it would be great if it were a value of 0, but that often causes Solver to fail because it's not possible to achieve a value of 0. So I usually just choose to minimize it. And next, the cells that we're going to change are the fitting parameters. And that's all. So now we solve. And Solver found the solution. Great, what could be better? Unfortunately, that solution doesn't look like it's a very good fit to our data now, does it? And that's because Solver couldn't deal with this exponential term, and so it just set it to 0 and kind of like drew a line that's basically the center of mass of that data set. Not acceptable. So let's try this again. This time we're going to put a constraint onto that parameter b, and we're going to say that it has to be, we could say it's less than equal to 0, but it'll just return to 0. So let's just say less than or equal to -1. Okay, and now we can try solving again. Ooh, no feasible solution. So in this case, we could think a little bit more about how to get our initial guess as close as possible to the measured data. But if you haven't cottoned on, actually this example is spurious. I chose an exponential because, you know, it could be credible. But the fact that Solver fails, in this case, indicates that the data were not taken from an exponential form. In fact, I was using a logarithmic expression. So let's put that here. All right, and we'll expand it out. So this is the actual expression I used to create this model set of data. And now let's change our model again. Okay, we'll propagate that through. I made the cardinal mistake of not using $signs to hold the fitting parameters constant. There we go. And now we're no longer using this C variable, so I'll just delete it for the time being. Let's see if we can get this initial guess relatively close. Yeah, pretty good, right? All right, and now let's try solving. Okay, and Solver has remembered our objective from last time. We're going to remove the constraint because we don't want it. And we're only going to change these two cells. And now we wait. And what we get is a reasonably good fit to the data. And so that is how you can use Excel and the Solver functionality to solve any, well, not any, but any simple nonlinear problem. So I recommend that you go out and try doing this with your data set if you have data to fit. And if in fact what you're doing is modeling, well, I guess you'll kind of be doing the reverse of this, where you're actually constructing the measured data using your own model. Either way, I hope this has been useful, and I will see y'all later. Bye.